Welcome to Lesson 13, Momentum and Impulse, one of the most powerful ideas in physics because it's always conserved. Here's the plan for today. Momentum is mass times velocity, P equals mv, measured in kilogram meters per second. And because velocity is a vector, momentum is a vector too. Direction absolutely matters, which means in a one-dimensional problem you must pick a positive direction and give anything travelling the other way a minus sign. Let's think back to Newton's second law. Force equals the rate of change of momentum, delta p over delta t. If mass is constant, the change in momentum is m times the change in velocity, and dividing time gives you ma, so F equals ma falls straight out of it. The momentum version is the more fundamental statement, however. Rearrange that equation and you get impulse. Force multiplied by the time it acts for equals the change in momentum. That product, F delta t, is what we call the impulse. And there's a neat graphical version of this. If you plot force against time, the area under the graph is what we call the impulse, and therefore the change in momentum. That's handy because in a real collision, the force isn't constant, it spikes and falls. The area, however, still gives you the answer. This is where the physics becomes life-saving. In a crash, your change in momentum is fixed. You're going at some speed with a constant mass, and you're going to end up at zero. Nothing will change that. What you can control is how long the change takes. Look at the equation. Force equals change in momentum over time. If delta p is fixed, then increasing the time decreases the force. So a car is designed to crumple, an airbag that inflates, or a crash mat under a gymnast. All of them do exactly the same job. They extend the collision time, and in doing so they shrink the force in the whole body. Same momentum change, longer time, smaller force. That's the whole principle. Now the big principle. If there are no external resultant forces acting on the system, the total momentum before an interaction equals the total momentum after it. For two colliding objects, that's m1u1 plus m2u2 equals m1v1 plus m2v2. The u's being the velocities before, the v's the velocities after. And I'll say it once more because it's a classic mistake. Momentum is a vector. If one trolley is moving left, its momentum is negative. Set your positive direction at the start of the question and be ruthlessly consistent with your signs. Finally, collisions come in two flavours, and the difference is about energy, not momentum. In an elastic collision, kinetic energy is conserved. The total kinetic energy afterwards equals the total before. However, in an inelastic collision, kinetic energy is not conserved. Some of it is lost, turned into heat, sound, or the energy of deformation as things bend and crumple. But here is the fact you must not lose. Momentum is conserved in both. Always. Elastic, inelastic, it doesn't matter. Kinetic energy is the thing that may or may not survive. Momentum always does. And to check which type of collision you've got, just calculate the total kinetic energy before and after, then compare. That's the end of the video. Next time we'll look at work, energy and power. Thanks for watching and check out my tutoring page below.